Good afternoon. Can you hear me? Good. First of all, thank you all very much for coming. I'd like to welcome our own students from nuclear science and engineering and other members of the community here at MIT, and also visitors, I think, from elsewhere, including, I understand, visitors from the Japanese community here in Boston. And I want to begin by expressing on behalf of the department and the whole Institute community my deep sympathy and condolences to the people of Japan, to our students and colleagues from Japan, for the awful events of the last few days. I think many of us here have great admiration for the courage and fortitude of the Japanese people. And we wish you only the best for this extraordinarily difficult period. I think many of our students may not know that there's a long history of close ties between MIT and Japan. A history that goes back as far as 1878, when the first Japanese student graduated from MIT, and he went on to lead the Mitsui group in the early part of the 20th century. That relationship between MIT and Japan continued and deepened throughout the decades, and beginning 30 years ago, Japanese companies and others in Japan started accepting MIT students as interns, which was the beginning of the Japan program, MIT Japan program, which ultimately became the MISTI program. That was not a customary practice for Japanese companies at that time to accept American student interns, but they understood the importance of this for our students and to their own aspirations to become more internationally active. And that cooperation with MIT helped usher in, as I said, a much broader program of international internships and in fact helped to change the way we think about education here at MIT. And we owe a great debt to Japan and the people of Japan for that reason. And I think not just because of this, but for many other reasons too, many of us would like to do something to help. There are many options, but let me just say, because I happened to see my friend Gail McGovern, the president of the American Red Cross, on the television last night. She said that if you text Red Cross to 90999, it automatically donates $10. So some of us might want to do that a couple of times. Now let me tell you a little bit about what we'd like to do this afternoon. It's really a simple goal. As a service to our students and others in the community, we want to try to provide some technical information on the nuclear reactors that are in distress, on what may have happened, and on what the options may be going forward. Obviously, this is an ongoing situation. There's a limited information, there are many uncertainties, and we're in uncharted territory in many respects. And so what's said here is, by definition, going to be incomplete. And some of the information we provide will have considerably larger error bars than our students have a right to expect in the classroom. But our judgment was that despite these limitations, it still made sense to go ahead and have this discussion. We'll see if we were right. I want to introduce our panelists. Let me just say, we'll go in the order that they will talk. Mujib Kazemi, who's second from the left there, is director of the Center for Advanced Nuclear Energy Systems in the department. He is also the TEPCO Professor of Nuclear Science and Engineering. To his left, Mike Golay, also a Professor of Nuclear Science and Engineering, works on risk and reliability in nuclear systems. To Majid's right, Ian Hutchinson, who's a professor of nuclear science and engineering and my predecessor as department head. And to his right, Bill McCarthy, who's the radiation protection officer of the nuclear reactor lab here at MIT, also deputy director of the environmental health and safety unit here. And also, possibly on the phone, although I don't see a phone, Jackie Yanch, who's in Spain. Jackie, are you there?
Yes, I'm here.
Fantastic. Until last year, Jackie was a professor in the Department of Nuclear Science and Engineering. She continues to be affiliated with us, and she's a specialist on radiation health effects. I'm just looking around the room. There are others who I know have valuable information and expertise, and I'm not going to hesitate to call on you as the discussion goes on. Now, we're going to begin with a brief overview of the situation. We're going to do three things. We're going to have a short description of the reactors that are in trouble at Fukushima Daiichi. We're going to have a very brief description of the events that have led us to where we are today, as best we understand them. And then we're going to have a very brief description of the current status of these reactors. But the main thing we want to do is to have an opportunity for Q&A and discussion. We've been sort of taking in a lot of information, much of it, I'm afraid, not very good. But really what we wanted to do here was to create an opportunity for people to ask questions and discuss the situation. The only ground rules that I'd like to impose here are that we will really focus primarily on the technical issues here, the issues that are concerned with the status and future of these reactors. There may be an interest, I think there probably will be an interest on the part of some in what this means for the future of nuclear power. We will discuss that if people want to do that, but I'd like to defer it until the latter part of the session. I'd like to make sure that we have an opportunity to focus on the technical issues here. So with that as background, I'm going to turn it over to Majid, who's going to tell us a little bit about the reactors at Fukushima Daiichi.
Well, I was told that I have about 5 minutes to tell you about them. Usually it takes about a couple of hours in one of engineering. Oops. All right. Many of you know that boiling water reactors are the majority of reactors that operate in Japan. Unlike the United States, where we have roughly 2/3 of our reactors are pressurized water reactors, only 1/3 boiling water reactors. In Japan, it's 60% BWRs and 40% PWRs. The reactors in Japan are both on the East Coast and the West Coast, and you see that in the map here. And you see that, in fact, there are two Fukushima plants. The one in trouble is called Fukushima 1 or Fukushima Daiichi, and has 6 reactors with 2 planned for the future. The characteristics of these reactors is that they are mostly from the very first vintage of BWRs that have been commercially installed. The Fukushima 1 through 5 has a containment, which is also of the very first design for such things, and I'll show you some slides about it. It's called the Mark 1, MK1. And they range in power from 500 megawatts, which is the first one, to about 800 megawatts for the fifth one. And then the latest addition, which is 6, went up to about 1,100 megawatts. What's interesting about the unit that got in trouble, Unit 1, was that it was scheduled to be shut down within this month. So the time lost, wasn't that much if you think about it this way, although with much trouble they're trying to stabilize the decay heat removal. Now, normally, heat is removed by circulation of water. Let's see, which one should I point to? Maybe this one. What is the difference between the PWRs and BWRs is that steam is formed within the vessel, which has the nuclear fuel that's called the core here. So that, roughly speaking, about 1 unit out of 6 out of the coolant that is circulating would turn into steam, which then is dried and sent to the turbine. The other 5 units of the 6 will be circulating within the vessel mostly, although there is a small part that is circulating also outside the vessel with the help of these pumps. So PWRs have a lot of water besides what's being turned into steam to power the turbines, and that's one of the good things about them. Typically, control rods are inserted from the bottom in these BWRs, not from the top, because the top has all these other gadgets to dry the steam and remove the water from it. In routine operation, the steam would go into a turbine, then will get condensed and will be returned into the upper portion of the boiling water reactor, and will then join the recirculating water within the vessel to form the total coolant flow. When it is shut down, the BWR has a different circuit to remove the heat, because there is decay heat that's generated in the core, and this additional circuit has a smaller pump, and it usually could be powered by AC power from the grid, or diesel generators if needed to be, to supply the heat for it. And what this small portion of heat is due to the fact that you have fission products that are decaying, and they decay with time, but roughly it takes an hour or so to reach about 1% of the total operating power. And it takes probably another 6 hours to 7 hours to reach 0.5% or so. So today, after a few days, we are under 0.5% of power in the cores that got affected. The containment, Mark I, is shown here. It has a characteristic of having a pressure-capable steel vessel called dry well, because it doesn't have any water, that's connected via tunnels to the suppression pool, which is also a pressure containment system that has a large volume of water. And that suppression pool is like a donut that goes around the bottom here. And it has enough water that it can condense all the steam and keep the pressure from going up when it has the water. Now, these features, of course, sometimes are inaccessible because something happens. But if there is a release of gas or steam, mostly, from the vessel into the dry well, it will find its way into the water. It'll get condensed there, as long as the water temperature is low. This is another cut that shows the construction a little bit better. This is the wet well with the suppression pool, and you can see pieces here of the dry well. And you can see that there are other structures. Particularly important probably is to notice that the spent fuel is stored in the upper regions of this building, and the refueling implies that the fuel will have to go from the core up and then down into this pool. And I will not comment on the events that have taken place because that's part of the other speaker's talk, but during questions and answers, I could clarify anything that you would like. Thank you.
don't know.
Can you make it go full screen? Okay, hello. My name's Ian Hutchinson. I have a personal investment in following the events that have been going on in Japan because my daughter-in-law and her family are from the Tohoku region of Japan. I'm pleased to say they're all safe, but it's naturally something that's exercised my mind. So I've been following the timeline of events, and my job is to try to outline what we know and perhaps some of the things that we speculate have been going on at the reactor. And that's what I'm going to try to do. Again, I want to emphasize that these are subject to major uncertainties. We're piecing together the information as it comes out. Quite a lot has been released, but quite a lot is unknown. So really, I'm just going to go through a timeline of what we know happened. The times here are in Japanese Standard Time for convenience. They're 13 hours ahead of Eastern Summer Time, this should say. We all know, of course, that there was an earthquake. It was an earthquake much larger than was expected. That earthquake and the tremors that accompanied it automatically triggered the reactors 1, 2, 3 to shut down. And they did so, so far as we know, on an automatic basis successfully. Reactors 4, 5, and 6 at the Fukushima 1 plant were not in operation. They were in routine maintenance, and so they did not have power. At that same time, the plant was cut off from the grid, so it had no external power. And to the best of our knowledge, the backup generators, which are routinely held ready in these plants, started. But something like an hour later, the tsunami hit. And it was the tsunami which did the most serious damage both to the plant and to the surrounding countryside and infrastructure. And in particular, it knocked out those multiple backup generators and indeed the connections to the pumps. In italics, I've put in my sort of commentary. As Mujib explained, the fission reactions are shut down once the reactors scram. That's what happened when they automatically shut down. But the afterheat, which comes from fission reactor products, is still continuing, and it requires continued cooling and circulation. But of course, at that time, once the tsunami had hit, there was no power for it at the site, and the country was devastated. So it was very hard to access the plant. In fact, there was some coolant circulation which continued at reactor 2, as far as we know, on battery power, but it didn't continue at reactors 1 and 3. And what therefore happened is that their coolant starts to boil away, building up pressure and eventually uncovering the fuel. If fuel rods are uncovered, then they heat up from the afterheat until eventually, at a high temperature, the zirconium reacts with the water and steam and gives rise to hydrogen. Eventually, if they continue to heat up, they will also melt. At 2100 that day, evacuation to 3 kilometers radius was ordered. The following morning in Japan, pressure was released from reactor 1. This was done deliberately in order to manage the pressure in the vessel and the containment. There was a small amount of radioactive emission, and that was confirmed by TEPCO at 10 a.m. The evacuation of residents in a 10-kilometer radius was underway by 3:30 in the afternoon, and shortly after 3:30, there was a hydrogen explosion in the building of reactor 1. So when the reactors are vented, the pressure is reduced. That hydrogen, which we presume was generated by the zirconium reaction, is part of what is vented. And it seems that this built up to levels in the reactor, which when mixed with the air, led to an explosive mix, which was set off for reasons which we don't understand. There are various safety systems that should have prevented this from happening. They clearly did not prevent it from happening, and we've all seen the videos of that explosion. Not long after, the evacuation zone was extended to 20 kilometers radius. Actually, on the morning of Sunday, the main thing that happened in the official timeline was that Unit 1 was declared to be a level 4 accident. That's the level that's just one below the level of TMI. Since then, the seriousness of the accident has progressed substantially. Actually, what happened during Sunday appears to have been substantial efforts to get circulation and cooling going again, but these were insufficient, and it was decided to pump in borated seawater to flood the primary containment. On Monday at 11 a.m., so this is now on the third day, there was a hydrogen explosion of reactor 3, which we understand was a consequence, again, of a controlled vent of the hydrogen from that reactor. 11 people were reported injured. But like reactor number 1, there was apparently no breach of the containment. The containment is that region that Mujid showed you, which is intended to prevent release of radioactive material in times of accident or difficulty. In the meantime, reactor 2, which had up until that stage been cooled or at some level, was found to have fuel rods, what is reported to have been fully uncovered. So reactor 2 no longer had successful cooling, and that it began to experience these difficulties, and they quite soon began to inject seawater, borated seawater. In fact, it seems like they got water in and then it came out again. It's been attributed to various different problems. The most plausible is something about faulty valves, but you may have heard of people talking about fire engines running out of fuel and so forth. The information coming out about that is somewhat garbled, and we don't really know exactly what happened at this stage. At 6:14 a.m. on Tuesday, that's today, of course, but since they're 13 hours ahead of us, that was quite a while ago now, there was a third explosion. This was in reactor 2. This was inside, as far as we can tell, inside or near the containment. And it seems that the pressure suppression system was damaged at that time, and as a result, the containment was breached. It's unknown how great that containment breach is, but it's a very bad thing because it means that there's a much greater opportunity for the escape of radioactive material. Until that time, the radiation releases had been quite modest. It's very hard to know the exact level of radiation, but one report said that radiations at the plant reached 8 millisieverts per hour, which is a substantial risk to plant workers, and plant worker evacuation began. Another worry that arose was on that same day was that the reactor 4 building, reactor 4 is adjacent to reactor 3, was observed to be aflame. And this was sort of at the same time that radiation levels were increasing further. There was a lot of suspicion that this fire was in the spent fuel pool. However, since that time, TEPCO has said that there was an oil leak in a water pump, and that was what was the cause of the fire at reactor building 4. By the way, these fuel pools are 30 feet deep. They're in the reactor buildings, but they're outside the containment. It's okay for their water to boil, but the elements must remain covered. If they uncover, they're likely to overheat. TEPCO says that the fire, or said on one occasion that the fire was extinguished at noon, so that's not very long after. IAEA says that they were informed that the fire was extinguished at 5 o'clock in the afternoon. So that's really where things stand, and I'm going to leave it to the next speaker, Mike Golay, to sort of bring the threads together. But I thought I would put up, at any rate, this table, which really just reminds you of the fact that there are 6 reactors. Most of reactors 4 through 6 are in good shape. Quite frankly, reactors 1 through 3 have all got very serious problems with them. Mike.
How do I get out of print stuff? I want to get out of this one. Yeah.
was the source of your data?
And
A lot of
here.
it comes from Wikipedia. I gave you the URL on the first slide if you copied it down. There's been, of course, a lot of blogging. We've also had material from friends and colleagues around the world sending us announcements, releases from the NEI, and so forth.
Okay, what I mostly want to speak about is the aftermath and things that you might pay attention to in terms of what's coming up. I'll add two things to Ian's presentation. And that is, as he noted, the tsunami was very important in taking out the backup power source, the diesel generators, and thereby contributing or creating a station blackout event, which is, he's already told you, is very serious. Another aspect of the tsunami was apparently there was flooding of switchgear connections. And so in order to restore electric power, it's not sufficient to simply bring in generators because you have to hook them up. And so pumping out some regions of the plant that became flooded is also part of the recovery. But a thing to look for is when do they recover electric power? And so that'll be part of it. The other thing is Ian alluded to the fire engines, which appear to be an improvisation by which the seawater is being introduced into reactor vessels, perhaps the suppression pools. And the ability to keep these fire engines running and pumping is also crucial to stabilization of the plant. What I want to do, though, is focus on the site and some of the transport of radioactive material that might be important. And so I'll use this one over here. So this is a partial map of Honshu, the main island in Japan, with blow-ups. Going down to finally showing you the site of the Fukushima #1 unit. And I want to put the evacuation zone in some perspective. And so the evacuation has been ordered up to 20 kilometers, so it's a little bit larger zone than is shown in the drawing here. There you can see it a little bit more. And so what we have is a coastal plain which is heavily populated, and then mountains behind it. The good news is that the prevailing winds are westerly, and so far that's where they've been blowing. This is important because the radioactive material that comes out of the plant basically will be carried by the weather, whatever it is. And as long as it's blowing out to sea, the health effects can be expected to be limited regardless of how large the radiation release is. The effects at the plant for the workers are a different story, but for the general population, that's what you would pay attention to. And then I assume we'll have a website for this, and we'll put this in some of the towns nearby are noted. And this will give you a better idea of closer in. This is an 8-kilometer radius, and so the 10 kilometers, which was the first evacuation, is here. There's some population center up here, down here, and some along the coast. And so now we've had sheltering ordered out to 30 kilometers, and so that's somewhat beyond the scale of what's shown here, with evacuation out to 20. So that's roughly here. The people between 20 and 30 kilometers are free to leave should they wish to, but what they've been told to do is take shelter, stay indoors, and keep the windows closed, don't use air conditioners, basically don't introduce air from the outside. Okay, in terms of the two power plants, you can see they're both in Fukushima Prefecture. #1 is up here, #2 is down here. They both have been reported to have suffered some damage from this earthquake, but what we've been hearing about is primarily Fukushima #1. And they're separated by 10 kilometers. This is an aerial view of the Fukushima site. You can see it's right on the coast. It has an artificial harbor, which is used for running the power plant there. But this is why they were vulnerable to both the seismic motion and the tsunami, because they're right there. They are reported to have had barriers to protect against the tsunami, roughly 2 meters high. And these were overtopped by the tsunami and led then to flooding at the site. So this is another view of it. The square boxes that you see here are actually the reactor buildings. These are the turbine buildings, and the others are auxiliary buildings. You can see the proximity to the sea, I think, rather clearly. And these are views of damage following I don't know which of the hydrogen explosions, but you can read the labels for yourself. This is the number 2 site. They have 4 reactors there, and we're not hearing much about it, so we don't really know what's going on, except that vaguely in the early days of this event, we were told that there was some damage there. But you see, it's essentially the same kind of construction right on the sea with an artificial harbor. And that's as much as I have to say. I'll stop here.
Okay. Thank you, Mike. So that was just really introductory information. I think at this point we would like to invite questions from the floor. There are a couple of mics set up here, and I would just ask that questions be real questions, actually. And if possible, make sure that there's only one question and try to make the question short. So please.
Yes, I understand from reading some of the documents this afternoon that they're supposed to be probably addressed to Professor Majid, I'm sorry, your last name? Kazim. Probably addressed to you. There is some sort of a steam-driven emergency core coolant system capability that's part of that design. How come that never took over or was ever involved in this process?
Yeah, that's not very clear, but in Japan in particular, they introduced this steam-driven pumping capability, basically, very early as an additional safety measure. And it is possible that the connections that bring the steam to that turbine, which then will generate the electricity for the, it may have been disrupted by the quake, or it may have been affected by the tsunami. It was never explained. Furthermore, I do think that in this case, only 2 out of the 6 reactors have it. It's not uniformly applied. It was applied in the early days, and for some reason, they didn't apply it at the later construction. And well, the third method for powering the pumps was the batteries, which had only a few hours of lifetime.
Hi, my name is Keith Yost. I'm a graduate student here at MIT. I have bachelor's degrees and master's degrees in nuclear engineering. And actually, Professor Goulet is my former thesis advisor, so hi, Professor Goulet. I have multiple questions. I can get through them very quickly and then just allow you to answer whichever one of them you think are appropriate and that you have answers to. Is it okay if I ask multiple questions?
No more than 3.
All right. So I guess question 1. In the 24 hours following the earthquake and plant shutdown, when and for how long were units 1, 2, and 3 without pumped coolant flow? Question 4, TEPCO reports that it's cooling the reactor cores using their makeup water condensate system, but also reports that they've been injecting seawater into the primary containment. And this has introduced some confusion because it's unclear whether or not the primary containment is that what they refer to as the area between the containment and the reactor or the reactor vessel itself. What are they pumping seawater into, and what is the proper nomenclature here? And then finally, what in your assessment is the current state of units 1, 2, and 3? Has the clad been damaged? Has the fuel been damaged? Is the reactor vessel intact? Is the containment intact? And are they being adequately cooled? Thank you.
All right. I think that might have been a technical violation. Okay, on the first question, the period for which the fuel appeared, how long has the fuel been uncovered? I think that's your first question.
The answer is we don't know how long they had no power. We have very little information about electrical powering to the site. Of course, they've been cut off from the grid since the first quake occurred, but the extent to which they have local power and the extent to which they have the ability to connect it, which Mike Goulet referred to, is very unclear.
Yeah, let me see something on
Go
that.
ahead.
It appears that they lost backup power when the tsunami hit. There was damage to the fuel tanks for the generators prior to then, and the tsunami essentially took out the fuel supply and flooded the electrical connections. As I've understood it, the tsunami came within about an hour of the initial motion, and the remaining cooling then was provided by boiling off water that was already available in the primary cooling system, but it wasn't because water was flowing.
As a quick follow-up, when was cooling reestablished then? When did they get power back? Or,
Well, that's the injection of the seawater, basically just flooding it and letting it heat up and evaporate.
Okay, can you hear me?
But Keith
Yes.
also had a question, which I think is an important
they're
one.
doing it.
Where exactly are they injecting the salt water? Is it coming into the containment, into the pressure vessel, which of course it is, or where else in the plant is salt water being introduced? I think that was your question.
At this point, to the best of our knowledge, salt water exists in the vessel as well as in the containment. So in the vessel, so that the fuel would remain cool, and in the containment, so that the suppression pool, which reached boiling point at some point, would come down and would be able to absorb the and condense the steam, and therefore keep the pressure down.
I'd like to follow up Keith's question, if I can, with a question concerning the longer-term implications of having salt water in both in the primary circuit and in the secondary or the primary containment. And there may be others here who might have comments on the longer-term materials implications of having salt water in these systems. But let's start with the panel. Mike.
Basically, the plants that have the seawater in the primary coolant system are write-offs. They're gone.
I think the next question, though, is what are the possibilities for long-term degradation of systems in that plant in terms of containment of radioactive materials?
I don't want to say anything. I don't know.
I can only relay an opinion expressed by our expert in the department, Ron Ballinger, who, when he heard that salt water was injected in the primary system, said that this will definitely create a degradation mechanism, and it's a matter probably of weeks before something gives in. This is based on his assumption of what the material, the type of steel is.
I think there may be other colleagues in the materials area who might have some comments on this later, but let's go on this side next.
Hi, I'm a student from Japan and a former student at Harvard, and I took a nuclear warfare classes and I passed it. I aced it. Yes. And I have some guys from Japan who wants to ask, what would be the worst case scenarios? It seems like those are the smoldering dirty bombs, and then size of. Do you have any conjectures to what would be the sizes and the consequences of that, like several 18-wheelers? Size of radioactive materials, or because TEPCO is not releasing any info, and then, yeah, so.
Okay, who wants to deal with that one?
Let me take a crack at it. First of all, what we already have is damaged fuel in these reactors. So there is a possibility of releases as long as the water level is not controlled and it comes down below the fuel damage. So there would be releases. Otherwise, the water is a very good way to contain a lot of the fission products and keep them there. Now, if for some reason the pumping of water is lost for a long period of time, not just for a short period of time, this would precipitate melting of the fuel. Remember now, the fuel power is only at a fraction of a % of the normal power, so it's not a fast process. And molten fuel would be relocating downward, and most likely, if there is water in the system, it will be downward because the steam would go upward. So there will be a process by which there will be some relocation, and when the water is reached, there will be solidification again. So it's not likely that we will see an explosion that in any way compares to the explosion of the Russian reactor some time ago. But there will be the possibility of releases that are sizable. And most of those are likely to be volatile materials, particularly iodine and cesium.
Okay, next question.
Actually, that's exactly my question. What are the health impacts from the release of the radiation? We heard in the early days that, it's relatively modest for the venting that happened, but now that there's been this breach, what should people be concerned with? And if you could compare it to, things that people understand, like taking a flight or a trip to the dentist or whatever, that'd be useful. I don't think a lot's been talked about in terms of health.
Let me take this opportunity, if she's still there, to call on Jackie. Jackie, are you still there?
Yes, I'm still here. Can you hear me?
Yes, very well. And
Okay,
so can
well,
everybody
I'll
else.
I'll address the release that seemed to have occurred today. Earlier this morning, there seemed to have been a release at the plant. The dose rates inside the plant were quite high, but outside of the plant, and certainly a couple hundred kilometers away in some of the bigger cities, the dose rates were very low. For instance, in Tokyo, looking at some of the dose rates that are listed in news reports on the web, the dose rates were about 20 times background for a fairly short period of time in the morning, and then they dissipated quite quickly. Other prefectures were measuring dose rates 30 to 40 times background. Now, just for some perspective, as the questioner asked for, Japan has a background dose rate that's fairly similar to the dose rate in America. And at the dose rates they were measuring in Tokyo this morning, you'd have to experience those dose rates for a few days before you would have the same dose as a simple chest X-ray. And that's really a very, very low dose. Flying to Tokyo, say, from Boston or New York, you'd get about 4 years' worth of natural background. And you're receiving that over many hours, but it's equivalent to 4 years' worth. And like I say, in Tokyo today, it was only a few days' worth. You'd have to live in Tokyo. You'd have to live with that dose rate for a few days to get even a chest X-ray. So the contamination levels at this point in time are very, very low. And we have no evidence of any health impact of those dose rates.
Thanks, Jackie. Bill, do you have anything to add to that?
No, what Jackie said was essentially correct. Right now, the radiation levels that are elevated are restricted to the plant site themselves, and the reports that are coming out are fairly consistent in terms of what the levels are. They're either changing or they're just not giving, they're giving data that is from different areas of the plant. But there are some high levels that are being reported, but off-site and definitely where the populations are now, it's very safe.
Yeah, just perhaps to add to that, the one individual dose that has been reported of an actual individual was a worker who received about 10 rem, apparently, which is twice the annual occupational limit in Japan. And people have asked, what are the implications of receiving 10 rem? And one explanation that was given, which I think was quite helpful, was that if this individual is a typical member of the population, he would have something like a 1 in 4 chance of contracting cancer over the course of his life. The effect of 10 rems would increase that chance from 25% to something like 25.3%. That's a 10 rem dose, and it's considerably larger than anything that's been reported close to the site boundary. Mike.
Yeah, let me just add one other thing concerning the releases, and they come in 3 categories. Noble gases, which come out very easily. These are primarily xenon and krypton. They don't deliver high doses, but they're highly mobile. Volatile fission products, which is most of what you would be concerned about. These are elements which will be vapors at the temperature of damaged fuel, and then later will condense into aerosols, but can be transported like fog in the atmosphere. And so iodine, cesium, strontium would be examples of these, and these are the ones of greatest concern. And then you have the non-volatile fission products, which by their label stay within the fuel. And to get them out, you have to transport the fuel out, as happened at Chernobyl when the core was basically dispersed. You pay attention primarily to the volatile fission products in this.
Sir.
My understanding is that the design of this reactor is such that even when it's scrammed to shut off, there's still a few percent of the output power that is being generated through decay heat. Is this unique to this reactor design? I know it's fairly early, or do modern reactors still suffer from this same problem, requiring external power for cooling even after they've been shut off? Thank you.
Majid, would you like to?
Yeah, it's not really a design feature. It is more of a natural phenomena that comes with the fact that some of the fission products are unstable and they decay with time. And that decay essentially is giving off radiation, which becomes the source of energy once absorbed somewhere. So all fission processes will result in some decay power. And as I said, the decay power starts at roughly 7% or so of the operating power, but within 1 hour it's down to 1% and further down. So all reactors have to engineer a way to remove the decay heat, and perhaps the modern reactors have paid a little bit more attention to sizing of the equipment so that there will be more margin. But from day one, it was known that decay heat removal is part of the design of any nuclear power plant.
Sir.
I'm asking, what is the status of the simulation tools, numerical simulation tools that have been developed for decades to study the failure of piping systems, steel pressure or concrete pressure vessels, and whether such tools exist at MIT or they have been used right now to simulate various types of scenarios in Japan? Thank you.
Thank you. Majid, would you like to, or Mike, whichever.
No, you go ahead.
Ben.
I might bring in risk assessment if you want to go there.
You know, I think simulation tools have increasingly been used and have become more accurate, you know, with time. But I can't say that the assessments of the consequences of what happens in a natural disaster depend only on the accuracy of the tools. It is the input to the tools that has to be known to be able to generate the right answers. And predicting the right acceleration of the ground, the right frequency of the pulses from the seismic and the aftershocks, it's all an art that cannot easily be determined. So I would say the methods themselves have improved, and they certainly give us the right output if we know how to precisely give them the right input. There are many nuclear faculty members in the audience. They can add to this if they know something about the status of the Japanese tools.
Mike, do you want to add to that?
Well, the only other thing I would mention is that in the last 30 years, using techniques which actually originated from our department, risk assessment methods have been used internationally in trying to understand the vulnerabilities of nuclear power plants. And so it's a version of a simulation tool, and it's been pretty well recognized that there are some earthquakes that are so strong you can't defend against them, and the one that occurred in this case was in that category. That is, the vulnerabilities to tsunamis, to ground motion had been recognized. And in setting the performance requirements for power plants internationally, the standards are lower than than would have protected against this earthquake. That sort of leads into a recognition that I think you have to understand the importance of this thing, which is it's a very rare event. The last time in Japanese records that I'm aware of that something like this happened was about 1,200 years ago. So you need to have some perspective. And our plants are designed to similar standards. If we have the same earthquake here, we would probably see damage to them as well. And I think we understand that and understand why.
Yeah, but we should qualify that by emphasizing that it was the tsunami that did the most serious damage to these plants, not the earthquake. They seem to have survived the earthquake tolerably well. So insofar as many plants are not subject to tsunamis, they're not subject to that kind of risk.
Right, but I would say that the vulnerability to tsunami was recognized.
Yeah,
what was
absolutely.
different here was
it's
that
part
the
of the
tsunami was
assessment
so
of
much
every
bigger.
nuclear power plant.
Can I just ask a follow-up question?
Yeah, go ahead.
Why build at the water event and not higher? It makes transport easier, but the tsunami wouldn't have hit if you built a power plant up at an elevation.
So the question was, in view of the obvious vulnerability to the tsunami, why were these plants built right by the ocean? Why weren't they built at a higher elevation?
It's a reasonable question, and I'm sure it will come in for re-examination because, well, I'm not trying to make a joke. If you look, the Japanese plants tend to be clustered by the sea, and they had tsunami barriers as opposed to building them up a hill. I can't answer why they made that decision, but they could have also elevated the backup power sources and provided the same thing, but didn't do it. I can't tell you why.
Yes, sir.
It's going to be a naive question, but once the power was lost to the cooling systems of reactors 1, 2, and 3, was there any possibility that power could have been restored to them by starting up one of the 3 reactors that was not running?
Oh.
No, because there was no power system infrastructure to do it. And our understanding is that the reason predominantly that the cooling was not able to be used was to do with, as Mike alluded to, the switch yards being flooded and so forth. So the quick answer is no.
There's no way to have a mini grid that was just inside the plants.
But
not on that time scale.
I think the other comment is that it takes a long time to start up a plant, and they needed cooling immediately.
Yeah.
That wouldn't have worked.
Okay, thank you.
Yes, sir.
Okay, I'm Eduardo Castle, Professor of Environmental Engineering. I have both a comment and a question. The comment is, I find it peculiar that these power plants have been sited on the Pacific side of Japan, right next to the subduction zone, capable of generating very strong quakes and also very strong tidal waves. On the other side, on the western side of Japan, they would have been safer. I suppose it has to do with some specific decisions. And my question is, given that power plants are designed for rare events, a magnitude 9 earthquake in that area doesn't seem to me like a very, very rare event, actually. It's more like 1 every 100, maybe 200 years, but not every 10,000 years, which is more or less the criterion for designing power plants. And given that these very strong earthquakes can take place, it is also known that they do generate very strong tidal waves. How come the auxiliary generators and everything peripheral to maintaining the safety of the plant was not designed against this massive tidal wave?
So maybe we can take these there are really 2 questions there. I think the first question is, was it reasonable for a for a decision to have been made that 9 was a beyond design basis earthquake? I think that's your first question.
One could reasonably argue that the magnitude 9 is not an uncommon event. I mean, it happens every 10 years or so somewhere in the world. Oh, no? Look, I mean, last year in Chile, there was magnitude 8.8, 8.9 also, in February of that year. In 1960, Chile had the mother of all earthquakes, 9.5. Alaska in 64 was also around 9.2. I mean, it's not such a rare event. I mean, you're talking of decades, not of centuries.
Well, in a specific location.
I'd like to take that one. First of all, this clearly is a rare event as far as Japan is concerned. Secondly, the devastation that has been wreaked in Japan far beyond this reactor is enormous. We know that there are tens of thousands of people that have been killed by this. And so we ought to keep this in perspective. This reactor accident and difficulty is a very serious matter which we as nuclear scientists and engineers have expertise in and are very interested in, and of course it excites interest in the public. But we need to keep it in the perspective that this is a natural disaster of immense proportions for the Japanese people, and our hearts frankly go out to them, not just in respect of the reactor, but in respect to the devastation that's been yielded everywhere.
No, I would fully agree. And my only point is that given that we designed for very rare events in terms of the quake itself, how come the same criterion wasn't used for possible tidal waves?
Okay, so I will comment, maybe Mike will comment because he looked at this at some point, but you know, the philosophy has been, which was adopted probably first in the United States, but then propagated to other parts of the world, that we design nuclear power plants to be able to remain operational if there is a reasonable expectation that the seismic event of a certain magnitude will occur during their operation. So there is something called the operation seismic event, and that, roughly speaking, an expectation of about 90% within 50 years to 100 years. Then there is the safe shutdown earthquake requirement, which imposes the requirement that the plant be able to shut down on its own once you have that kind of earthquake. And they design it up to an expectation of 1,000 years, roughly speaking, with some approximations. So, in fact, the plants did what they had to do, which is to shut down safely. But the complications of the tsunami, because the tsunami was also much higher than was known to have happened before, I think that complicated the matter for them.
Okay, yes, next question.
My name is Alexander Cooper, graduate student in NSC department and previous student at the University of Tokyo. Before asking my question, I would just like to emphasize the point of Professor Chinton and remind all of you that about 200,000 people in the Fukushima region were evacuated, and a few more millions in the north part of Japan are now suffering from a lack of food, difficulty of access to water, electricity and transportation, and also about 10,000 were reported either died or missing. The Japanese community has already mobilized itself downstairs gathering donation, and sincerely hope that after this conference you will take the time to go downstairs and give whatever you may give. My question, I have actually two questions. The first question is, it seems that in the recent concern are also about the spent nuclear fuels. Could you discuss more about what is happening with those spent nuclear fuels in this they were in the pool, and then also Japan is expecting about probably a 50% of afterquake in the following days. What is the risk related to this afterquake if it happens?
So each reactor has a spent fuel pool into which the spent fuel is unloaded, the used fuel is unloaded, and all of those reactors, all 6 of those reactors have some fuel, as far as we know, has some fuel in their pools. And of course, there's a substantial amount of fuel there. So if some accident occurred which somehow began to release the fission products from that fuel, that would enhance the severity of the event. There was a concern at one time when there was a fire at Unit 4 that fire was caused by some damage to the spent fuel pool of reactor 4 that had caused its spent fuel to become uncovered. In that event, it's possible for melting and fires to arise from that. The latest word said that that was not the cause of the fire, but frankly, we don't have detailed up-to-date information about that. The main concern is that the spent fuel is not within the containment chambers. So if that fuel melts, the potential for the volatiles to escape is much greater.
If I can just add to that very briefly, there are two things that make the problem of the spent fuel easier to deal with, and one thing that makes it harder to deal with. The harder problem is the one that Ian has just mentioned, the fact that the fuel is not inside the containment. The two easier problems, or the two easier aspects, are that the fuel pools, although they have, in most of these reactors, quite a lot of fuel in them, perhaps as much as 10 years worth of spent fuel, by this time are not generating as much heat as obviously the fuel in the core. So for example, in units 2 and 3 of the reactors at Fukushima, those cores are probably still generating on the order of 10 to 12 megawatts. Whereas a reasonable estimate of what's in the fuel pools in the reactors is perhaps on the order of 1 megawatt. So it's an order of magnitude. Plus, you've got the advantage that these fuel pools are at atmospheric pressure, so it's a lot easier to introduce water into them. You can actually just run a pipe into them, as opposed to the problem of cooling the fuel in the reactor vessels, which are still, as far as we know, at above atmospheric pressure, and therefore you need pumps, of course, to get the water in.
My name is Florian Metzler. I'm a student of technology and policy. The Japanese utility, TEPCO, and also the Japanese authorities have been criticized by some for not providing enough information at the rate that is desired by some of the media, for instance, and maybe not at the precision that is desired. Whereas I can understand that it's not possible to brief the media every half an hour, as they may probably expect. So I would like to hear your opinion on whether, to which extent you think the flow of information to the public is acceptable under such circumstances, or it could have been improved, or it should be heavily criticized, or it's actually laudable in a sense.
Well, if I can just start that, I mean, I think, it's quite difficult for those of us who don't speak Japanese to assess the effectiveness of the communications in Japanese. The written communications that are being provided in English by Tokyo Electric Power, I would have to say, are limited. And during some of the most difficult parts of the crisis, I would say also sporadic in their frequency. Having said that, I would add that I think one has to have a certain humility when it comes to expecting a Japanese company to communicate everything in English. I think we have to recognize that that may not be their highest priority. But the evidence that we also have from Japanese who are trying to follow events in Japan and elsewhere is that even in Japanese, the information has been somewhat parsimonious. Now, there's one other comment that I think probably ought to be made about this, and I think probably my colleagues would agree with this. It may not just be because the company or the government is unwilling to communicate information. It may actually be that the people on the ground, the people in the control rooms in these reactors, actually are having trouble figuring out what's going on. And if that's the case, it wouldn't be surprising if they were not getting a great deal of information in Tokyo at the headquarters of these large organizations. I don't know whether others have anything to add.
Yeah, I tend to think that under the chaotic situation that must exist there, and the fact that there is no way to be able to enter every corner of the plant to know what's going on, it must be difficult to make statements that you can stand behind. So probably, and rather than sending a bunch of speculative ideas about what might happen, they are waiting to make an assessment that they can stand behind. compared to some previous modes of behavior, I would say this time I sense that TEPCO is making a deliberate effort to be upfront and not silent about events. They have been issuing updates when things occur, like you have a new explosion and you need a new explanation. In fact, the updates would come. But in between, there were occasions where things were quiet, and they have issued statements that things are under control. We'll have to wait, I guess, and see at the end, what's the overall assessment. But from what I can see and from the actions of the government there, that depends on what TEPCO information is provided to them, they seem to be taking precautions in order not to cause harm to the public as a result of this accident.
Let me add just a little bit to this. You guys are all too young to remember 3 Mile Island, most of you. I remember giving a lecture at Amherst a few years ago, and I referred to 3 Mile Island, and a student said, "Professor, what is that?" So that was good news. The thing that's really different about this time, Mujib alluded to, is we're not getting the media feeding frenzy that we went through with Chernobyl and 3 Mile Island, and we're not getting the sort of the spontaneous generation of alarmist speculation and misinformation. So I'm
getting it, you saying?
we're not experiencing what we had experienced with some of these previous nuclear emergencies. To the same degree, it's a question of degree.
It tells you how bad it was.
Yeah, if you hadn't been through the other, you wouldn't make the contrast.
I mean, it seems like the impatience of the media leads also to a distortion of the public perception of what's happening. Would you agree?
Well, let me just go to the last point I wanted to make. One purpose of the parsimony with the information being given out may be also to avoid, particularly in a very crowded country, exciting fears that might not be justified. Because in the end, they probably are going to have to evacuate large numbers of people beyond those that have already been dealt with because of the direct earthquake. And managing that well is still a problem that faces them. And I won't be surprised if that's a factor in all of this.
All of that said, I do think we have to recognize that there is, I think, growing frustration in Japan about the limits to the communication that's going on. I don't know. I don't have the ability to assess that, obviously, but I do think we have to recognize that there is a somewhat higher level of frustration, even within the last day or so, about the information. I hope that that will be taken care of. Yeah.
I wonder about the timescales of this drop-off in decay power. We've heard the 1-hour estimate and the 6-hour estimates, I think, but clearly the amount of time which will elapse between an earthquake and a tsunami are to some extent proportional to the distance to the epicenter. I would think that that was a pretty big component, and so if you had the tsunami quite a bit earlier, you would have a different situation. And at the same time, we ask, well, what is happening right now with the decay and what percentage are we at? I thought that you said a generation on the order of 10 megawatts right now. Is that correct? In reactor 1 and 2 or 2 and 3?
In the larger reactors, probably it's about 10 megawatts thermal.
I thought we heard a 1% after 6 hours estimate over here.
0.5% after a day. And that's because the reactor generates about, these 700 or 750 megawatt electric reactors are generating about 3,000 about 2,400 megawatts thermal because of their thermal efficiency of about 33%.
Okay. Having
second law.
Given that, what ideas do you have about if the tsunami had come a half an hour earlier and if everything was to shut off right now with a little bit of water in the tanks? What are the speculative notions here? I'd appreciate that. I don't know if anyone feels comfortable giving me those ideas.
I'm not really sure I understand. You're saying if the tsunami occurred earlier, would that have resulted in a different situation in the plant?
Presumably the heat output would have been substantially higher at that time. If it gave out a half an hour in as opposed to an hour in, you're talking about...
Well, there's a rule of thumb for how the decay heat varies. I think at this stage it's going like the 1/5 power of the time. So sort of minus 1/5 power of the time. So that's how it's falling off. So if you want to calculate from now on, that's roughly how it goes.
Cool. And on the front end of things, if the tsunami had come after a half an hour, would we potentially be seeing a much more serious thing had the epicenter been closer, or is that just crazy?
I think the answer is no, but...
A little worse, but basically it's the integral of the power. It's the energy released, and so you can figure out the difference. It would exacerbate things to some degree, but qualitatively, I don't think it's going to make a difference.
Okay, cool.
So my question actually relates to the very slow decay that's happening now, and it's obviously the first few days has been very bad, and we all hope they can get it under control and there won't be a massive release, like Chernobyl, for example. But then the question is, what happens in the longer term, weeks, months, years, that you have to manage this spent fuel and the reactor contents? Can you speculate or discuss what happens going forward to deal with this in this badly crippled reactor situation? What are the options? What ultimately will happen?
Well, again, those of us who remember TMI remember that after the melting, let's say partial melting, I think roughly about 20-25% relocated to the bottom vessel. Right now, TMI has been completely cleaned. In fact, it was cleaned within 10 years of the event. And all the fuel with contents of the radioactivity in it was moved to Idaho, where it's stored. So you can recover from those accidents. It takes an effort to make sure that the workers do not get exposed to the radiation. But it is possible to clean up the place if that is the intention.
I'm just wondering, in the current situation, though, where much of the infrastructure has been destroyed in the surrounding country, I mean, in the area of where the earthquake and tsunami hit, I don't think it's the same as the 3 Mile Island situation, where basically you had the plant, but the rest of the infrastructure was completely unaffected, I'm assuming, other than the plant itself.
Yeah, look, the key thing is getting electric power back. It may take time to get the grid back because of factors that you cite. The ability to get backup power sources, though, is potentially there because they have this artificial harbor, they have access from the sea, and they have the nation's resources to apply to it. So I'll be surprised if it takes them more than a week or two. But, you know, the future is always surprising.
Okay, I think we're getting, we're past the time we're supposed to finish. I think we can take one more question, maybe two. But let's make them quick.
Can you advise us what advances there have been in the management of decay heat technology since the design of this reactor in particular? I'm curious whether there are reactors that can cool themselves using their own decay heat, or...
It seems to me that if you can get air to naturally circulate to remove decay heat, that would be a technological goal for future design so that you don't depend on pumping water in. It is very difficult to do, however, when you have a situation that doesn't give you a continuous path for the heat to flow. Therefore, some people believe that gas-cooled reactors, which in fact have a solid moderator as opposed to water which can evaporate, would enable the decay heat to be removed to the vessel, and then if air can circulate around the vessel naturally, then the decay heat can be removed naturally.
So with 3 Mile Island, the hydrogen ignition didn't seem to be an issue. Why is it such a big issue with these plants, and how is hydrogen getting out of the primary containment into turbine buildings and igniting?
Hydrogen was a big concern at TMI, so it was actually rather similar. There are big differences in the plant layout, and obviously the explosion that occurred at Fukushima was in part a function of the fact that the venting was into this building in which it was possible to build up an explosive mixture. The details of whether that could have happened in a PWR and the extent to which it did, I'd leave to my other colleagues.
Yeah, let me say something about that. Basically, the hydrogen was produced at 3 Mile Island, as Ian has said, and here. The thing that's different is in the boiling water reactor system, you have safety relief valves, which are part of the control system, and they are able to vent coolant, steam that is, and any gases associated with it into the vapor suppression pool, which is part of the containment system. You don't have that function in a pressurized water reactor, and so the issue did not arise in 3 Mile Island. In order to avoid overpressurizing the containment, what I've been told is that the operators vented the containment and let the hydrogen out of the secondary portion of the containment and into the spaces of the reactor building that led to the explosion. That venting can also be done with our reactors, but my understanding is that the ducting takes them outside of the reactor building, and so it's a difference in design and practice. But the purpose was to keep the containment building intact.
The last, I would add one thing, that in general, the buildings and the containment in particular around boiling water reactors are much smaller in volume than around pressurized water reactors. So the same amount of hydrogen would be vastly diluted in a pressurized water containment, and that will make a difference.
So according to the plausible future scenarios, could you please discuss if there can be long-term contamination, and if yes, on what sort of area and surface?
Jackie, are you still there?
I'm here. I'm sorry, I didn't quite get the question.
The question had to do with what are the prospects for long-term contamination in the area around the reactor? I think that was the question.
In terms of the amount of release or the consequences of a release? I mean, there's been very little that seems to have been released and dispersed beyond the containment vessel. However, if things get, if more radionuclides are emitted, if there's a larger release, then the people in the area are facing either permanent or many-year relocation or living with elevated cesium-137 levels, which has a 30-year half-life. It will probably dissipate a little bit quicker due to rain and erosion and things like that. But it's got a very long half-life, and it's the primary radionuclide that you're worried about from this kind of event. And I don't actually know what kind of what the rules are in Japan for for allowing people to return home. In America, the EPA recommends not returning home until the dose rates are down to about 2 rem a year, which is very, very low, and only a fraction of what you would get, say, from a CT exam of the chest or the abdomen. So it remains to be seen how much is going to be released. If there is a major release, then they're looking at long-term contamination, and the problem is going to be the cesium-137, which gets deposited on the ground, it gets into the water table, it gets into the food, and animals eat the grass contaminated with cesium, etc., and it gets into both the agriculture and the livestock. And depending on how large that area is, they could be looking at massive evacuations, or, like I said, figuring out that they will need to live with elevated radiation levels for a long period of time. Now, unfortunately, we have very little data, almost no data about how much radiation we can live with in terms of elevated background levels. All of our data about the health effects of radiation come from a situation in which all the doses delivered in less than a minute. And so we just don't know how much radiation can be, what kind of contamination level can be considered safe. I mean, some parts of the world are at natural dose rates which are 40 times the dose rates we're living with, 40 times the dose rate Japan has as a natural background level, and no adverse effects have been noted. But as I say, there has not been a careful study of just how much is too much. And there's going to be a trade-off between having people leave their homes forever or for long periods of time and living with an elevated background level. And we don't know whether, we don't really know, like I said, how much is too much to live with.
Okay. I'd like to just make one note, which is that the students of the Nuclear Science and Engineering Department have started a technical information blog which is addressing a number of the issues that have come up in the discussion today. And you can get to it, just go to the NSC website, and it's actually attracting rather a large amount of traffic. There's a lot of interest in these questions, obviously, around the world. And our students have taken the initiative to establish a blog which I think can be a very valuable contribution to the debate. All I'd like to say at this point is to thank my colleagues for their excellent responses to the questions, and to thank all of you for taking the trouble to be here. Thank you very much. Of Nuclear Science and Engineering. To his left, Mike Golay, also a professor of nuclear science and engineering, works on risk and reliability in nuclear systems. To Majid's right, Ian Hutchinson, who's a professor of nuclear science and engineering and my predecessor as department head. And to his right, Bill McCarthy, who's the radiation protection officer of the nuclear reactor lab here at MIT, also deputy director of the Environmental Health and Safety Unit here. And also, possibly on the phone, although I don't see a phone, Jackie Yanch, who's in Spain. Jackie, are you there?
Yes, I'm here.
Fantastic. Until last year, Jackie was a professor in the Department of Nuclear Science and Engineering. She continues to be affiliated with us, and she's a specialist on radiation health effects. I'm just looking around the room. There are others who I know have valuable information and expertise, and I'm not going to hesitate to call on you as the discussion goes on. Now, we're going to begin with a brief overview of the situation. We're going to do three things. We're going to have a short description of the reactors that are in trouble at Fukushima Daiichi. We're going to have a very brief description of the events that have led us to where we are today, as best we understand them. And then we're going Good afternoon. Can you hear me? Good. First of all, thank you all very much for coming. I'd like to welcome our own students from Nuclear Science and Engineering and other members of the community here at MIT, and also visitors, I think, from elsewhere, including I understand visitors from the Japanese community here in Boston. And I want to begin by expressing on behalf of the department and the whole institute community my deep sympathy and condolences to the people of Japan, to our students and colleagues from Japan, for the awful events of the last few days. I think many of us here have great admiration for the courage and fortitude of the Japanese people. And we wish you only the best for this extraordinarily difficult period. I think many of our students may not know that there's a long history of close ties between MIT and Japan. A history that goes back as far as 1878, when to have a very brief description of the current status of these reactors. But the main thing we want to do is to have an opportunity for Q&A and discussion. We've been sort of taking in a lot of information, much of it, I'm afraid, not very good. But really what we wanted to do here was to create an opportunity for people to ask questions and discuss the situation. The only ground rules that I'd like to impose here are that we will really focus primarily on the technical issues here, the issues that are concerned with the status and future of these reactors. There may be an interest, I think there probably will be an interest on the part of some in what this means for the future of nuclear power. We will discuss that if people want to do that, but I'd like to defer it until the latter part of the session. I'd like to make sure that we have an opportunity to focus on the technical issues here. So with that as background, I'm going to turn it over to Mujib, who's going to tell us a little bit about the reactors at Fukushima Daiichi.
Well, I was told that I have about 5 minutes to tell you about them. Usually it takes about a couple of hours in one of engineering.
She said that if you text Red Cross to 90999, it automatically donates $10. So some of us might want to do that a couple of times. Now, let me tell you a little bit about what we'd like to do this afternoon. It's really a simple goal. As a service to our students and others in the community, we want to try to provide some technical information on the nuclear reactors that are in distress, on what may have happened, and on what the options may be going forward. Obviously, this is an ongoing situation. There's a limited information, there are many uncertainties, and we're in uncharted territory in many respects. And so what's said here is, by definition, going to be incomplete. And some of the information we provide will have considerably larger error bars than our students have a right to expect in the classroom. But our judgment was that despite these limitations, it still made sense to go ahead and have this discussion. We'll see if we were right. I want to introduce our panelists. Let me just say, we'll go in the order that they will talk. Mujib Kazemi, who's second from the left there, is director of the Center for Advanced Nuclear Energy Systems in the department. He is also the TEPCO professor, first Japanese student graduated from MIT, and he went on to lead the Mitsui group in the early part of the 20th century. That relationship between MIT and Japan continued and deepened throughout the decades, and beginning 30 years ago, Japanese companies and others in Japan started accepting MIT students as interns, which was the beginning of the Japan program, MIT Japan program, which ultimately became the MISTI program. That was not a customary practice for Japanese companies at that time to accept American student interns, but they understood the importance of this for our students and to their own aspirations to become more internationally active. And that cooperation with MIT helped usher in, as I said, a much broader program of international internships and in fact helped to change the way we think about education here at MIT. And we owe a great debt to Japan and the people of Japan for that reason. And I think not just because of this, but for many other reasons too, many of us would like to do something to help. There are many options, but let me just say, because I happened to see my friend Gail McGovern, the president of the American Red Cross, on the television last night,